All right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. Thank you for tuning in today. We're going to take a look at entropy this afternoon. Entropy is abbreviated as delta S, and without getting too complicated into what entropy actually is, we're just going to say that entropy is a measure of disorder. Right? And so if you think about your room at home, the more disordered your room becomes, the higher the entropy of your room is. We can also look at it as a dispersal of matter. All right, and so our technical definition that we are going to be working with in this particular class is entropy is a measure of disorder and dispersal of matter. So the more unorganized my matter becomes, the more my matter becomes spread out, the higher the entropy values are going to be. So a couple of things about entropy is we understand from the second law of thermodynamics that the entropy of the universe, the disorder of the universe, is always increasing, and that is the thermodynamic favorability that we've been talking about and hearing about is really that drives everything. It's this increasing disorder, right? This increasing chaos that is driving the favorability of a lot of our actual reactions, right? And so what we need to understand about this also and how we're going to relate it in this class, it is a state function, all right? Entropy is a state function. You need to understand that, and that should be sending off those lights and those bells in your head, and you should be saying, oh, well, enthalpy was also a state function, i.e. we can use Hess's law. It's a molar value. We can sum reactions to get an overall delta S value. All right, and so you need to understand that those same kind of methods that we're using to calculate these delta H values, we can also use to calculate delta S because of the fact that it is a state function. It doesn't matter how we get there. It's just the difference between beginning and ending. All right. The other thing that I want you to make sure that you get down is that the more dispersal, the more complicated the matter, the higher the entropy. You need to understand what the actual number is telling us and what the difference is telling us. So if the number becomes more positive, that means my entropy is actually increasing. All right. And so the biggest example, or the one that you probably can relate to the most, is if I start drawing a solid versus a liquid, and these are diagrams that we've all seen before, right, versus a gas where I've got molecules in high molecular motion moving very, very fast, and they're really far apart. We should understand that as I'm heading in this particular direction, that my entropy increases. And that shouldn't be any stretch of your imagination if you've understood everything I've said up to this point, that entropy is a measure of disorder and dispersal, and that the more dispersed or complicated, the higher the entropy. Well, I'm going from solid to liquid to gas. My molecules are spreading out and they're moving faster, right? So I should expect entropy to increase. Now, gases have the highest entropy bar none out of the three states of matter. So gases, and we can actually clue in and focus in on the number of moles of gas in a particular system to kind of make a prediction about the overall entropy of the system. And so, for example, if I'm looking at something that has 4 moles of oxygen versus, let's say, 6 moles of oxygen, immediately I can look at that and say, well, this one has more moles of gas, right? Because oxygen is a gas. I guess I could just point that out and make that. But oxygen's a gas, so if I have more moles of gas, I have a higher entropy. And so this guy over here, I would make the prediction would have a higher entropy, or another way of saying that is a larger delta S, a larger entropy value. All right? And because of this, we can actually use this to predict the sign of my delta S for reaction. So, for example, I'm going to bring up this old example here where I've got the combustion, the combustion of water, or I'm sorry, the combustion of hydrogen. Learn how to speak here. So the combustion of hydrogen, right? I'm looking here. I know everything's in its gaseous state. Everything is in its gaseous state. Make Haley proud here and draw my G's look like G's. All right, so on this side, I've got 3 moles of gas. On this side, I've got 2 moles of gas. Notice the number of moles of gas is going down, so I could make a prediction on this and say that my overall entropy value is actually going to go down because the number of moles of gas actually decreased. All right, and so that's how we're actually going to be able to predict the overall entropy without actually having to do any calculations. This is just a real quick, is it going to be a positive or a negative change? All right. Okay, the next thing I can look at here is molecular complexity. And what I mean by that is if I've got NaCl versus CaCl2 versus sugar, which is C6H12O6, I can tell and look, just seeing this, that my molecules are becoming more complicated as I'm moving to the right. And so again, we understand the more complex or the more complicated my molecules become, the higher the inherent entropy value of that molecule. All right? And it has to do with the fact it's just got more moving parts. We see these as individual elements, but we have to understand each individual element has electrons in motion, it has molecular vibration and molecular motion in and of itself. So the more complicated. All right, is essentially the easy way to think about that. And so molecular complexity is also a way that we can look and say, comparing one to the other and just say, hey, the higher the molecular complexity, the higher the entropy value. Another thing that we can take a look at is solubility. Right? If something is going to dissolve, it's going to go from a solid state to an aqueous state. We have to understand, if I go back to that beginning drawing that we did, if it's in a solid, all the molecules are really packed in close together. A lot of the times there's some organization with that. And so when I dissolve it, that all spreads apart, right? So I've dispersed matter. I've increased the entropy, right? There is one particular exception to that, and those are carbonates. When I dissolve carbonates, they actually arrange the water molecules, right? They cause some arrangement of the water molecules in solution, and they actually will reduce the disorder. And so that's a weird thing about the carbonates that they actually do. If you're going to dissolve a carbonate, a lot of the times you're actually going to see a reduction in entropy, not an increase in entropy because of the dispersion. All right. So, and what I'm talking about here, sodium chloride, right? I've got it. I'm going to break it to, let me do this right, Na plus and Cl minus. So again, I'm separating the ions. I've separated, I've dispersed the matter. I'm increasing entropy in that general fashion. The other thing, and I'm going to write this really big, generally increases in temp increase disorder. So an increase in temperature causes an increase in disorder. All right? I hope you remember this from your pre-AP days, a statement called heat 'em up, speed 'em up. Right? Hopefully you remember that. And what we're going to do is we're going to take a look at a particular distribution. This is called a Boltzmann's distribution. And what I'm going to do is I'm going to pause the video and I'm going to go ahead and draw this out for you. All right, and so I've got the Boltzmann distribution drawn out. I suggest that you actually just pause the video and get it sketched out as well, because we're going to talk about it, and I'm going to have you notate a couple of things on here. So the first thing to see is that it's actually a comparison of the number of molecules and molecular speed. What I don't have labeled on here is that this is at a particular temperature, right? Each temperature has its own little line graph on there, and you need to understand that the majority, when we talk about temperature being a measure of average kinetic energy of the molecules, then what we're talking about is you have to understand it's an average. I have some that are moving really, really fast, but I also have some that are moving really, really slow, but for the most part, they're all kind of moving the same. All right, and you see that from the peak or the area underneath the peak in this particular case. So what happens when I heat them up? Well, we say heat them up, speed them up. So what does that actually look like on here? So if I were to heat this up, what happens is this curve actually flattens out. So now I get a less, or I guess more of a distribution of molecular speed, where I end up with way more molecules over here across this activation energy barrier. A lot more of my molecules are moving faster, and that's why we say heat them up, speed them up, right? And so we could say that maybe this was at 800 Kelvin. And so the big thing with Boltzmann's distribution is just to get a very visual representation of what that heat 'em up, speed 'em up means. And because of the molecular motion, right? That's why my entropy values will go up when I increase the temperature of a particular substance, because I've increased the speed of the molecules, and the faster the molecules, they tend to disperse and spread out more and more. All right. It's also because of Boltzmann distribution that we can argue, notice this isn't zero. I don't have molecules that are not going anywhere at all, right? And it's because of this constant molecular motion, the motion of the electrons, the vibration inside the nucleus of the protons and neutrons, that I will not have entropy values that will be zero, right? I will not have entropy values that will be zero because I have some kind of motion in molecules, whether it be nuclear vibration, down to the muons, gluons, quarks, and all that other stuff, that I have some kind of motion, I have some kind of entropy present in the molecules, all right? So you will never see, like your enthalpy values and your delta G values that you'll see, you can have values that are zero for elements in their standard state. No, you're not going to have entropy values that are zero. I need you to make that really big in your notes, all right? Okay, well, hopefully you got everything down without any questions, but if you did have some questions, you got those written down. I'll see you in tutorial for those, and otherwise I'll see you in class.